know where I am. Okay, so this is joint work with Michael Tëmkin and Jaroslaw Wlodarczyk. And there's parallel work by Michael McQuillan with his student Marzo with basically the same result. And we start with curves. So it's about resolution of singularities, okay? Yeah. So with curves, you know how to resolve singularities of a curve. To resolve a singular curve, you find a singular point. You find a singular point, you blow it up, and the beautiful thing is that something gets better. So it will always finish with a non-singular curve. Everybody starts with that, and this gives you the wrong impression about the general case, and therefore we all have a complicated relationship with singular varieties. So let's look at a surface. How do you want to resolve a surface? You want to, so surfaces are more complex, singularities are not just points, but you can still ask for the worst singular locus, and if you define the worst singular locus correctly, it will be smooth, and you can blow it up. And unfortunately, this in general does not get better. And the example, the classic example is the Whitney umbrella, which I want to draw. So this is the Whitney umbrella. It has a very special point here, known as the pinch point. And so if you follow the instructions in a previous slide, and we find the worst singular point, you know what the worst singular point. You ask this, it has a handle, by the way. So it really is an umbrella, not very useful, but you ask it, where is the worst singular point? It says, oh, right here. And so you're going to blow it up right there. And if you do that, you get into trouble. This is an image, a beautiful image that you can find on the web of the Whitney umbrella. So a slightly rounded version of that. So the origin is the worst singular point. There are 3 charts in the usual description of blowing up. And only the third one is interesting. The Z chart, we write X is 3 stands for the third chart, okay? Is x3 times z, y is y3 times z, and z remains z. You plug it in. Yeah. it's so disturbing. You get z squared times this. Z squared is just the exceptional divisor. You're happy to remove the exceptional divisor. But what is this? This is precisely what you started with. So you immediately get into an infinite loop, and you wonder if you want to spend any time with singular varieties ever again. Okay? So what do you do? Of course, you don't give up because you know, resolving singularities of surfaces has been known for a long time. So the classical solution of this issue, that if you just do what the surface seems to tell you, you get into a loop, is you remember more of what is happening. You remember the exceptional divisors, which is a very natural thing to do. You want exceptional divisors anyway for uses in geometric constructions. And you also remember the history, which is a real pain. So if you ever study this, nowadays there are reasonable expositions like Kollar's book, but still this is a pain. This makes the whole construction unpleasant. And as I said, we have a fraught relation with singular varieties of dimension at least 2. Nevertheless, how am I doing? Nevertheless, we have this result. So this is a theorem obtained together with, this is supposed to give me together with Tëmkin and Wlodarczyk. There's basically the same theorem by McQuillan with Marzo, and it's basically a weighted version of Hironaka's resolution singularities result. It's still in characteristic 0. So everything here is in characteristic 0 today. So I'm all right for now. There is a procedure, I call it F, you can imagine what F stands for, associated to a singular subvariety. So X is a singular subvariety of a smooth variety Y. So I'm doing embedded resolution. Associated to a singular variety, a center, I need to tell you what a center is. With associated blowing up, I need to tell you what the blowing up is. And a proper transform, so a proper transform of X is X prime, such that the maximal singularity invariant of X prime is strictly smaller than the maximal invariant of X. This is what Michael Tëmkin, my collaborator, calls the dream algorithm. You don't need to know anything about what you've done before. Take a variety, embed it in a smooth variety, look for its worst locus, do the right thing there, and it gets better. The dream algorithm. In particular, for some n, it will have to stop because I haven't told you, but the invariants live inside a well-ordered set, and therefore it will stop. I think this is what everybody wanted for the beginning, but knowing about the Whitney umbrella, people gave up. Yeah. Okay. On the other hand, there's a colleague. Oh, this I don't know how to stop it from shutting up. There's a colleague in France, Bernard Tessier, whose advice about resolution of singularity is when you have a singular variety, approach it gently and ask politely how it wants to be blown up, and maybe the variety will tell you. Okay, so the answer is if you do it right, you can do it. So I need to explain all the red stuff here, and probably more than the red stuff. As I said, okay, I already said this is the dream algorithm. So procedure here means a functor. You need to say which. Oh, you have a question.
No.
You need to say which on which category. Functor on which category. So this, or maybe this took over for some reason. On which category? I'll move the cursor. Maybe that's. No.
But that's just a laser. Does it not show on the wall?
No.
Oh.
It did show just a few minutes ago, so I did something wrong.
It's the big button, right?
Yeah, the big button. Oh, wait. Oh, there we go. So a functor on smooth surjective morphism. So the category is the smooth variety Y with smooth surjective morphism. So this says that if I have a smooth surjective map from Y1 to Y, then what I do on the pullback is the pullback of what I do on Y. This has huge implications. In particular, you never touch the smooth locus, because the smooth locus is obtained by taking a map to the point. And you never blow up the point because there's no point.
Y is smooth or not?
So the ambient variety is always smooth.
Okay.
Always.
Ambient variety is smooth. Okay.
Okay, so I told you what procedure means. I need to tell you what invariants are, what centers are, and what blowing up means in my context. So I'll give you a preview, and only later I'll give you a definition, because I want to show you that in the example it actually works. So I'll give you a preview and show you that it works in the example. So preview on invariants. For a point in my variety X, we define a number associated to the point, and we call it inv sub p, just not being very inventive. It sits inside a well-ordered subset of the set of sequences of positive rational numbers. So the subset is well-ordered, And we proved, this is actually in a previous paper, we proved that this is lexicographically upper semi-continuous. And further, if I have a smooth point on my variety, then the invariant is the minimum value and vice versa. So you get the minimum possible value if and only if the invariant, if and only the point is smooth. So it detects smoothness. And then we define the thing that appeared in the slide before. The maximal invariant is just the maximal invariant.
So maximum, usually it's kind of goes in which direction? So it jumps on points, or
It can jump up in points.
it can jump on a point?
Yes.
Okay. So and that is maximum. So that's the case when it is maximum. Yeah. When it's
So I'll take the maximum and the,
all points. Yes.
of all points of x.
Because when you look at some valuation, it's kind of open. No.
But this is the right thing.
Okay. This is right. Okay.
Trust me. Okay. So let me give you the example. Before I haven't defined the invariant for you, I will define the invariant for you. But we have an example, and the example tells you what you want to do. So x appears with power 2. The order of this ideal is 2. That's the minimum order. Sorry. The order of the ideal at the origin is 2. That's the maximum order over all points. But, okay, so the invariant here starts with 2. Y and z appear in a monomial of degree 3. So I'll put 3 for y and 3 for z. And I want to also say that this invariant has been in our arsenal for ages. If you look at previous treatments of resolution of singularity, this appears in there, except that there's all sorts of other junk involved in it which hid it. Okay, so what's wrong? How do you stop it from shutting down? I'm okay. I'm within time. I want to tell you about. So that's about invariants, the previous invariant. Let me tell you about the center. And the center is sort of is written in front of you. If the invariant is A1 through AK in the previous example 2, 3, 3, and it was defined using variables x, y, z in that example, then you take the first variable to the power A1, second variable to the power. So that's the center.
And k is the dimension of the ambient variety.
K is no, is where the invariant stops. K is at most the dimension of the ambient variety.
No.
At most. So you can think of it as you can add. If you want, you can add the value in infinity until you get to the because the invariant of the zero ideal is going to be infinity if you insist, or it would be the empty sequence in this. Anyway. So then you write. I'm defining for you a normalized center because that's what appeared in the slide of the theorem. So I rescale the powers here until they are inverses of integers, such that the integers are with GCD 1. So I just rescale it so that A1 through AK is L times a sequence of inverses of integers of GCD 1. That's a J bar. In our example, J is just what you read, x squared, y cubed, and z cubed, because they appear in those types of monomials. And I rescaled it so that the rescaled version has 1/3, 1/2, and 1/2, which is what actually appears in classical treatments of weighted blowing up. And I should say that this center has been staring in our face for a while. It's just that one needed to recognize it, and as usual with inevitable mathematics, it's not that one recognized it, but two recognized it in this case. I mean, McQuillan also realized that this works.
So wait, I missed this part. So this J bar is good for what?
This J bar stands for, I'll tell you what happens in the weighted blow-up, but the usual treatment of weighted blow-up, you want to put x1 in degree W1, so it's as if you have a W1 root. X2 in degree W2, as if you have a W2 root,
I see.
etc.
Okay.
I have to tell you what the center is. I mean, what does it mean to take fractional powers? So there's a beautiful way to understand it. That
One more question. So it doesn't depend on the coordinates, yes, in some way. So
the way I wrote it, it depends.
Depends, yes.
But when I say center, I'll define a center later, and the center
then it won't depend. Okay.
It won't depend. So now I want to go back to the example and carry it out and show you that something good happens. So now I'll do the blowing up of Whitney's umbrella with this center. So with this center, I write x is w is w3 times x. So again, only the third chart really makes a difference. The other charts are easy. So the 3 says x is w third x3, y is w squared y3, and z is w squared. Okay? You're taking the square root of z and you use it to define the weighted blow-up. It's important that I use the weighted blow-up in the stack-theoretic sense. Otherwise, I get into great trouble. Okay? So y prime is the thing which has coordinates x3, y3, and w, but the quotient as a stack, so it's still smooth. And the action is the way it has to be. So the root of z has -1. The root of y, since w squared appears, is acted trivially. And sorry, the y3 is acted trivially, and x3 is acted again with -1. So that's the ambient space. Let's see what happens when we plug in the equation to the umbrella. So I just plug in those coordinate to x squared. In x squared, I get w6x squared. In y squared, I get w4y squared. And z becomes w squared, so I can pull out w6. And lo and behold, I get something that is better. So I have an exceptional part, but this is now just a transverse intersection of two planes. It has invariant 2, 2, which the way I define the lexicographical order is less than 2, 3, 3. I don't.
So is the exceptional divisor regarded as a stack here then? It's like a
So the whole thing is a stack.
stack.
Okay, so. Right. So Bernard Tessier was right. He said you should ask the variety how it wants to be blown up. Not just, I mean, the variety told you where first, and you went ahead and tried to improve it, and then you had to correct everything for ages. Okay? If you just ask and listen carefully how it wants to be blown up, it wants to be blown up this way. So what I explained, one moment, X has begged to be blown up like this all along. That's what happened.
So the original variety that you described was reducible, right?
Yeah.
So it looks like in this equation it's reducible.
No, you're taking the stack quotient. So so X is acted by plus or minus 1. So as the stack quotient is
I see.
is still irreducible. There's no contradiction in mathematics.
Okay.
Sure.
At least so far I haven't found one. All right, so now I need to define things correctly. So that was an example, and now we know that something is happening when we better follow what the varieties actually ask us to do. Okay? Not mess things up. So we'll take first I'll define the blow-up of a reduced center, of a center of this form, where the wi are integers, and you just copy not what Harshon says when he defines the blow-up, but the comment right after that, describing the blow-up of space at a point. And you just follow that. So you take the image of, I define a sub-algebra of the stupid algebra with one variable, over OY. And I take the subalgebra where I throw in generator xi in degree wi. Okay? So this is not the actual algebra I use because I use the integral closure of it because in order to get things totally canonical I need the integral closure. But this at least explains what I'm doing and I can define things. So this is just a graded algebra. The graded algebra has an ideal, namely the positive degree part, defining the vertex of the spectrum. So inside the spectrum of the algebra I have the vertex. And the stack-theoretic proj, as it always has been, is the spectrum of the algebra minus the vertex mod out by the action of the multiplicative group given by the grading.
So when you say take integral closure, you just make it coprime divided by wi, yeah, by or something.
No. I mean, I'll tell you later.
Oh,
So
okay.
it's somewhat complicated. So
Yeah.
let's leave it for the end.
Oh, okay.
I'm sure there'll be more than one
Yeah.
question.
Okay.
It's somewhat more complicated, and it's worthwhile looking
okay.
at.
So it's not just that. Yes. Okay.
So Brandon and I worked quite a bit with sort of stack-theoretic proj in the one paper we wrote together. So this is just an abstract definition of a blow-up, and as you know from Marceau, you want to describe it explicitly. So there is an explicit description in charts, like we did in the example. If I have this center,
Yeah.
I look just at the x1 chart. The x1 chart, I just take a w1 root of x1. And for xi, I write a new variable xi prime by pulling out u to the wi. Just what you expect to have. This just follows from the algebra B. It's harder to the algebra B is useful in order to have an explicit description. Okay, so we have an induced action just by root of unity acting on u by multiplication by zeta, and then there's only one way the other things work out. So that's the blow up in one chart, and of course there are many charts, and you can check that they all glue together. They have to because they give you the stack-theoretic proj. There's also, maybe I should skip this. I don't think there's toric stack people in the audience, so I'll skip the toric stack, unless people actually ask for it. So let's. Is this the right place I want to be? Yes. Let's define. So I haven't told you how to associate to a subvariety of a smooth variety and a center. So now I only showed you one example. Now I'll show you how it works in general. So I'll show you. Sorry, I won't show you in general. I'll show you in an example first. A different example because this example shows you something interesting. So I'm taking this equation. With y appearing with here in degree 8, and so the invariant is actually associated to an ideal, and the natural ideal to take is the ideal of the variety x, which is in this case a principal ideal, but the ideas are the same. You define the first part of the invariant, the first entry in the invariant, to be just the order of at the point of the ideal. In this case, the order is 5 because that's the least order monomial appearing here. So therefore, the first part of the invariance is 5, and the center should look like x to the 5 and then something. I just need to tell you what the something is, and the idea is to try to balance different monomials with x to the 5 and see which one balances better. You can describe it in terms of Newton polyhedra, but that really confuses me. So let's just do it this way. To balance, the right thing is to balance this with this in this case, because y to the 8 is too big. So to balance x to the 5 with this, we need to balance the extra part, namely x squared, with the y part. And so this and this should have the same weight. And if I raise it to power 5 over 2 so that I get x to the 5, then x to the 5 and y to the 3 times 5 over 2 should have the same weight. In other words, okay, so 15 over 2 is less than 8, so this doesn't matter, this matters. And the center we should use is this. And here's the reduced center where I take the 1 over integers version. If instead I had the 7, then the 7 would take over, and this would be the center, and this would be. So this is just a sort of hand-wavy description. But once I have that, I can describe what happens in the blow-up. In this case, with this center, and in this case, with this center. Maybe I'll do just the first one. If I start with the first one with the 8 on top, and I use the center that I wrote before, x to the 1/3, y to the 1/2, then I wrote here the rules. X in the x chart, I have x is u to the has a cube root, and y is u squared times something else. I plug in and pull out the exceptional part, and I get this is smooth. In general, you won't get something smooth; you just get something of lower invariant. And if you look at the other chart, where you take a square root of y, again you plug in the power that you have here is going to be the same. Again, in this case, you got something smooth because I chose this to be a short example. So I need to tell you how to do this rigmarole in general. Here I just told you how to do it in examples. There'd better be a general way to do it. So we need to have some inductive procedure. So since we chose the first variable to be something that behaves behaves well here, I need to tell you what that is. What we do is we restrict to x1 equals 0 the data of all of these. So it's not enough to just take the ideal itself. Let's look at the example here. If I restricted the ideal, in this case I would get y to the 8, which would be the wrong thing. So I need to take something that takes into account all the monomials that appear here. Okay, so the right thing to do is to look at the ideal generated by all its derivatives, and so on up to the a1 minus 1, where a1, remember, is the order. If I took the a1 derivative, I would get the unit ideal, so it doesn't give me any more information. And I need to take them with the corresponding weights. So the classical way to do it, there are at least two ways to do it. One is using Grease algebras, which I will not discuss here. So the standard way that Kolar, for instance, uses is to form the so-called coefficient ideal of the ideal I with a given order A1 to be the sum of all monomials in the data that you need to consider, where the weighted degree of the monomial is at least A1 factorial.
But you're still with coordinates, yeah? You haven't left the standard coordinates. Yeah.
I chose the coordinate x1.
Yeah, that's all.
That's all I chose for now. So I chose something called the maximal contact,
Yeah,
and I will need to show you that this is independent of the choice.
Okay. That's okay. So the rest is in.
The derivatives are just derivatives,
I see.
and I restricted them to the particular hypersurface I chose.
Yeah,
And I need to show that it doesn't matter which
which
action.
is kind of minimal in this way, yeah? Even, okay, I just want to understand, okay. Yeah, okay.
All right, so this is known as a coefficient ideal. So f runs over all monomials whose weighted degree is at least a1 factorial. So this is an ideal whose order is not a1, but a1 factorial. And then you restrict that. So I2 will be a restriction of that to the hypersurface x1 equals 0. There's a choice here, and the wonderful thing is that this is independent of choices. So now I can tell you how the center and the invariant are together defined for a given ideal. So, okay, I already told you how A1 is defined. A1 is the order at the point where the maximal order is obtained of the ideal. X1 is a regular element in the A minus first derivative, any choice of a regular element. I know that there is one because the derivative of that contains 1. So there's some antiderivative of 1 there. Okay, so this is known as a maximal contact. And it's not at all clear that what I will say is independent if you just look at it, but there's an inductive procedure which says that. So then you write I2 as I did before, and suppose I2, now I have induction, right? I'm in a lower dimension. So I2 has it already by induction a defined invariant. And that invariant is defined with parameters x2 bar through xk bar defined at the point on the locus where x1 equals 0. Okay, so I lift the parameter x2 bar. Maybe I should draw a picture.
Yeah.
A picture would do. I think I'm done with the Whitney umbrella. I have a smooth ambient variety. I have a somewhat singular variety here. I have a point where the maximal order is obtained, and I have a hypersurface a smooth hypersurface, passing through a point which is maximal contact, namely it has it contains a scheme-theoretic locus where the ideal has order A1. So this is x1 equals 0. And on x1 equals 0, I can repeat the process and I have x2 and then x3, etc. So because I have induction on dimension, I haven't said that, but I have induction on dimension. So I can assume that I already defined for I2 the invariant and the parameters used for the invariant. I will lift the parameters in an arbitrary way to the ambient space. And then I define the new invariant. So remember, I2 was rescaled so that the invariant was, the order was A1 factorial, expected order was A1 factorial rather than A1. So I should divide by the factor A1 minus 1 factorial. And this is the invariant of my ideal, inductively defined. What I'm saying is that if you look at Kollár's books, this is in there. It's staring in our face. You have A1, A2, A3, A4, but unfortunately there's also, I don't know, California, Massachusetts, and all sorts of other junk in between that confuses.
So can these invariants be computed from the Newton polyhedron by looking at
Yeah.
slopes?
This is the lowest phase of the Newton polyhedra with respect to the best possible parameters. The parameters are not unique, but the slopes are unique. And here is the center, except that, as you can see here, even the AI are going to be rational numbers. We had an example, 15 over 2. So I need to tell you what this is. It's not an ideal, it's something else. But in the example, I know that it works. So in the example here, you calculate the coefficient ideal, you get some stuff with x, with a factor of x, which will vanish when you restrict, and then y to the 180, and then you divide by 5 minus 1 factorial, namely 24, and you get that the center is what I said it was. It's x to the 5, y to the 15 over 2. And in the second case, you just get 7. So it works out. That's actually the easier case. Still on time, I think. Yeah. Okay, so
It's the same, yeah?
what's that?
The same question.
Oh, sorry, this is a typo. This is an 8 and this is a 7.
Ah, okay.
This should have been a 7.
Yeah, okay. Okay, because it's just,
I think I forgot to update something in my.
yeah, okay, I just.
Yeah, you're right. Yeah, I know what I did. I took the slides from the wrong folder. Okay, I need to tell you what is J. So this is J is basically a Q ideal, and there are many approaches to Q ideals, and I like the definition that Michael Tëmkin proposed. You look at the Zariski-Riemann space of X, namely the set of all valuations. It's a topological space. It's a projective limit of all possible birational modifications of X. With this sheaf of ordered groups gamma, so every point here is a valuation ring. So there's a constant sheaf, which is a function field. There's a varying sheaf, which is the valuation ring at each point. The stalks are valuation rings.
Yeah.
If you take K star modulo O star, you get the valuation groups. That's the sheaf of groups gamma. These are ordered groups because valuations live in an ordered group. And so I tensor it with Q. So a valuative Q idea is just a global section of that. It tells you for each point what rational valuation you want to, what minimum of rational valuation you want to have in elements of the ideal.
A zero in the sense of topology of the risk, yeah?
Yeah.
Yeah.
Okay. And if you have a valuative Q ideal, you can define an ideal by taking all those functions on the original X, no blow-ups, whose valuation at every valuation is at least that value. And if you have, on the other hand, if you have an ideal, you can take its image here, basically, so which for each valuation gives you the minimum V of f runs over I. So there are only finitely many. So this is always a minimum is defined because you're taking a minimum over finitely many, infimum over finitely many elements. So a center is in particular a valuative Q ideal. So when I wrote x1 to the a1, etc., you take V of what I wrote, and that's a valuative Q ideal. So that's the right way of, that's one right way to talk about Q ideals on varieties. When interested in birational geometry. That's what the center is. Now we have to prove something.
So is this just a fancy way of saying a weighted blow-up, or is there other content here that...
No, a center can be something much worse than a weighted blow-up. Sorry, not a center. A valuative Q ideal can be much, but the center, yeah, so the center is an indication of where you want to take a weighted blow-up. So the particular centers I chose, the particular valuative Q ideal I choose for the centers are those that give you weighted blow-ups in the stack-theoretic sense.
Okay.
May I ask one more question?
Yeah.
So suppose you have not one point, but like a big variety of maximal contact.
Yeah.
So in a way you have to do this, how to say, you have to look at hypersurface which contains it, no?
Yeah.
Yeah, okay, so it's just all
Yeah.
together.
So when you so there's a so hypersurface of maximal contact exists locally.
Yeah, locally. Yeah.
but they don't exist globally. It's easy to see that they don't exist globally. So you need to show
yeah,
that the procedure is functorial. I mean, you have to produce a functorial procedure, otherwise you're stuck.
yeah, because
And in fact, if you look at Hironaka, that's what he did, except he refused to use the word functor. And if you asked him, yeah, it is functorial, but he refused to use
but
the
in
word
a way,
functor.
at the end, you will be blowing a subvariety of maximum contact. Yeah, something like that. Yeah, just to try to keep track. Yeah, okay. And you need to show it lies in a reasonably small subvariety.
Yeah.
Okay.
So so what centers I'm allowed to even consider are admissible centers. So you say that a center is admissible for a given ideal if the corresponding, so I'm equating a center with its evaluative Q ideal, but I compare that with the evaluative Q ideal associated to the ideal, and I say that a center is admissible if it's less or equal in the sense of the ordered group than the evaluative Q ideal, which if you think about it in terms of ideal, it means that this ideal on the Zariski-Riemann space contains this ideal, and the center is inside the zero set, the zero scheme of your ideal. And there's an important lemma which says that because the centers are defined so that I have weighted blowups, I can first go to the weighted blowup, in which case the center is divisorial. And when is a divisorial center smaller than an ideal? It's precisely when the ideal so the divisorial center is e to the power L. Remember the L, we said what power of my reduced ideal reduced center goes into the center. So e to the power L e is exceptional. E to the power L, it defines the total transform of the center, which is divisorial. So this is divisorial, and saying that this is less than or equal to this exactly means that when I go to the blow-up, e to the power L divides the ideal. Namely, there's an ideal I prime, so that the original ideal becomes e to the power L times I prime. That's an important lemma, but it's easy to, that's, when you work on a divisorial center, that's the only thing that can happen. There's only one valuation to check. We have a proposition that says that I can test whether a center is admissible for I if and only if this power of the center is admissible for the coefficient ideal. So I can always pass to the coefficient ideal, and the advantage of that is that this is what I'm going to restrict. And the point is that when I look at the coefficient ideal, I calculate. I go to the blob and I calculate which monomials appear in the derivatives, and I can't. The way I weighted the derivative ideals is such that they can't. They have to contribute at least as much order as the original ideal. So the part of the ideal is I to the power a1 minus 1 factorial, and this gives me the correct. So there's more to it, and so I wrote here a technical lemma, and I don't know if I want to actually. I'm doing fine, but okay. All right. So So the point about coefficient ideals is that they, in some sense, on informal coordinates, they remember everything about all the derivatives of the ideal at the same time in an organized way. So I can, if I have the order A1 and X1 is a maximal contact element, then I can write the coefficient. There's always going to be X1 to the power A1 factorial. And then the next term is X1 to the A1 factorial minus 1 times an ideal coming from the other variables. And these ideals are basically derivative ideals, and they behave well with respect to multiplication. So this is something that Pearson-Millman proved, that Wlodarczyk proved, that Collar proved. It's something that is well known about coefficient ideals, but it's technical and not very. So it takes 5 lines, but not the kind of 5 lines I want to give in the talk. So now the main theorems are that, first of all, the center that I defined for an ideal is always admissible, and the proof is just by induction. It's really, if you have gone carefully through Collar's book, you wonder how come we had to work so hard in the past. This is a paragraph. And then there's the theorem says that the coefficient ideals, the invariant of the coefficient ideal drops. So P prime is any point over P in the exceptional, and the theorem says that if I write C, the coefficient ideal, I forgot, the pullback of this should be times OY prime. I was careless. So Ci, so what's on the left should be Ci A1 times OY prime. The pullback of the coefficient ideal to the blow-up. As I said, it will pull out some power of the exceptional times C prime, and the invariant of C prime will drop. And so you see, dropping the invariant of C prime is equivalent to dropping the invariant of the original. Right? So let me just tell you a little bit about what goes into it. So on the X1 chart, the first term is X1 to the A1 in the description, in this description. So the first term is this. And this becomes exceptional. So on the X1 chart, you only have C prime equals 1. So this means that the only points where you need to care are on the X other charts, and only on the exceptional divisor, because that's where the points that are missed by the X1 chart. And then you have by induction that the invariant of what am I trying to say here? That the invariant of the what I called I0 here. So the restriction of this is really what I called I of 2 earlier. The invariant is at most A2 through AK. This implies that if you add the X1 and transform it, you get an invariant that at most is at most the given invariant. So this is just all I'm saying that this is an easy explicit computation. Yeah. So that's basically it. So I want to say if you go to a lecture in a conference on literature, then people read a paper, right? they literally read a paper, and then there's somebody like Fedya here whose role is to attack. Okay?
No, I'm not.
I'm not saying you did, but they give somebody the role of a responder, not. They give somebody the role of a responder. But in math, it's rare that you can read a paper. But the paper, I mean, I had 18 slides. The paper is 12 pages. So I essentially read the paper.
Yeah, okay.
So that's what I wanted to say. There's one more thing I can tell you, but for now, I mean, I do have time, but that's what I have to say.
Any questions?
Yeah, I have questions.
Of course.
No, I'm trying to understand. So my question is about, so first, essentially, you work with some kind of toric structure.
Yes.
So
But you choose the. So this is like so. There's a difference between tropical geometry and non-Archimedean geometry. So tropical geometry is for a particular toric structure, and non-Archimedean takes all possible. So we choose the best toric. We take the best facet of the non-Archimedean space.
Yeah. So, but you know, that's exactly what was the problem with moving to finite characteristic.
What was the problem?
Torus is more difficult.
Oh, these things are not ordered
Our
properly.
proof is Panty broke exactly at the point where you look at torus from point of characteristic 0, it's kind of k-pi, so it's the fundamental group is abelian. In characteristic P, it's a huge group, and that was a breaking point.
So,
So
you
when
were
Torus
asking,
is-
you were asking about characteristic P, right?
Yeah.
That's the question, yes.
Well, okay. So I met with. So of course, we were told by somebody who read our grant application that Michael was talking about this. Michael McQuillan was talking about this. So I met with Michael, and we had a great time talking for over a week. Part of it we talked. We just needed to realize we had the same result. Okay, different methods because we have Wlodarczyk and he basically uses other. Abianca's type of techniques. But we've spent most of the time thinking about currency. So there are problems with characteristic P. Some of the problems are not really serious, but some are. So it seems one issue is to define an invariant because you are supposed to take a toric stack, and you are forced to take a toric stack with possibly tame but non-reduced group scheme. And when you take a so giving you a non-separable quotient map. So if you have a non-separable quotient map, the invariants change. So it might be that all we can hope for from this method is something like local uniformization, but I don't know. I don't know. And so there are 4 people already think about it. Probably there will be more.
But is there
This problem is a hell of a problem. I mean, if you tried it, it drives you crazy. So I might be already damaged goods. Maybe some young person who has not been frustrated will solve it. But,
And second remark is that if you have a big variety of contact, then you may need to increase dimension of the big variety in order to embed into something smooth.
what do you mean?
No, if you need to blow up something of big dimension. Suppose you have a big variety.
This talk was all about embedded resolution.
Embedded, I see.
But sure, so there is an invariance under. So if you re-embed, you just change invariant A1 through A2, you just put ones.
Okay.
And it works.
Yeah, that's like that. Okay.
It's invariant.
Sure. Just pull up. Okay. No. Okay, great. Thank you.
So the weighted blobs, they do introduce some singularities in the ambient space. Is that right?
They do introduce some singularity in the coarse ambient space, but the stack is smooth. It's spec of a
Yeah,
of a polynomial algebra modulo in action, right? It's smooth.
I see. But,
So it's really important to work with the stack, at least for us. We would never have discovered this if we worked with charts on usual weighted blobs, because I mean you immediately go out of cyclic quotients. You would have to do.
But I'm sold. But
I know you are.
Yeah. But supposing that I'm an antediluvian person and I don't like stacks, so the singularities that you get, from taking the course space, there's a canonical mechanism for resolving those as well, right? I mean, that's
Yeah. So I guess the point is, if you want to resolve singularities in schemes, which is something that you want anyway, even if you accept stacks, right? So you have X, and I produce for you a smooth stack A1, X1. All right, so there is a procedure by Daniel Berg, which is called destackification. It says if I have a smooth stack, I can have a sequence of well understood, so these are stacky blobs. So blobs composed with root constructions, x1 prime, such that the map to the coarse moduli space is also nice. So x1 prime bar. So the coarse moduli space is also smooth. And since this is a variety, this is the resolution of singularity in the usual sense. This procedure is functorial, therefore you don't touch the bad point. So you can reduce the usual resolution of singularities without stack structure by using this beautiful result of Baird. Yeah.
So is this invariant well-defined in characteristic P?
That's exactly what I was saying before. In characteristic P, since we're using weighted blowups, let's say your weighted blowup has a mu p. So a mu p cover, the order of an ideal under a mu p cover might change. So it might not. Well, okay. So Michael, McQuillan, and I sat down in my basement and broke our head, hit our head against it. And okay, so there's nothing I can tell you now. I mean, this is a problem where if you don't have a solution, you don't have a solution. Here.
Yeah, you tried it many times as mine.
One last question. So, do you have any quantitative measures of how much more efficient your procedure is than the standard procedure? If I look at singularities of surface singularities of multiplicity 17, like how many blobs?
I think the difference is like the difference when you do the Euclidean algorithm for finding the GCD of two integers. Yes. You can divide and take the residue, or you can subtract the smaller number again and again.
Yes.
That's the difference. That's the difference.
So it's
There's a conceptual difference that not having California and Massachusetts and all that in the middle. It's sort of confusing you, but
it does dramatically reduce the number of steps.
It reduces the number of steps in a way that is akin to that.
Oh, I see.
So the point is that in the usual resolution of singularities, you have to sort of deal with the exceptional divisors before the invariant has a chance to drop.
Yeah, I see. But you don't.
The invariant immediately drops. So notice that we haven't dealt with logarithmic case. We do want to say something about exceptional divisors, but this will follow. I mean, students have to have thesis, right?
Okay. Well, thank Dan.